So we were talking last time about quasi-coherent sheaves. Um, and of course, we've already had this discussion about these board lights. No, there we go. Quasi-coherent sheaves. So could we get rid of this word quasi? You're much more likely to hear the word coherent sheaf than quasi-coherent sheaf. I mean, it depends a little bit on the context. Um, so what does this mean? Well, I need to make a few definitions. This is kind of recalling stuff from algebra. So, and a module M is finitely generated if there exists a surjection from a finite rank free module to M. Okay, great. This is just saying that there's a finite set in M, which is the image of the free generators here that generate M. It's a set. Another consideration is that you could say that M is finitely presented. So, right, this is talking about generators, but of course, once you choose generators, then you want to think about the relations between them. The relations between them would be generators of the kernel of this map. So I'm finitely presented if then the kernel of this map is also finitely generated. And a theorem, which is proven in Vakiel, it's a common kind of result. If M is finitely presented, so finitely presented means that there's one choice of these maps that makes this work. But if there's one choice, then actually for any surjective map from a free module, the kernel is finitely generated. For all surjections. Okay, and I should, tell you, there do exist modules which are finitely generated but not finitely presented. So for example, if A is not Noetherian, and I is an infinitely generated module, so a module that isn't finitely generated, right? Your Noetherian is a ring if and only if every ideal is finitely generated as a module, then a mod I is finitely generated, but not finitely presented. Because there's a surjection from a free module to it, whose kernel is not finitely generated. Yeah, sorry. Right. Yes, I meant ideal. I was saying it's not finitely generated as a module, which is the same as saying it's not finitely generated as an ideal. So exactly where you have to start worrying about all these definitions is in the case of non-Noetherian rings. Oh, yeah. Yes. I was about to get there because I'm going to define a third thing, which is also equivalent to these when you're Noetherian. Um, so the last one is we call M coherent if all finitely generated subs are finitely presented. So that means if I take any map from a finite rank free module to M, not necessarily surjective. So the image of that is a finitely generated submodule of M. I'm requiring that there exists a surjection of a finite rank free module onto that kernel. Okay, and indeed, we were just getting to this theorem. A is Noetherian if and only if finitely generated is equivalent to finitely presented is equivalent to coherent. All right, and we already saw one direction that if A is not Noetherian, there exist modules which are finitely generated but not finitely presented. And of course, if you're not finitely presented and you're finitely generated, then you're not coherent. So this is an example of a finitely generated module that's not finitely presented or coherent. On the other hand, so proof one way, because it's generated by one, right? It's a quotient of a finite rank free module. So this is a property of rings. So I'm saying that A is a Noetherian ring if finitely generated A modules are the same thing as finitely presented A modules are the same thing as coherent A modules. So I don't, right. Right. I mean, these notions are useful because even if the ring isn't Noetherian, the modules might have these properties, right? But you know, I mean, somehow like it's pretty tricky, right? This could be Noetherian as a module over A, right? Because somehow the badness is happening in A, not in A mod I, right? If I could, for example, take here A is, you know, the infinite polynomial ring, and I is the ideal generated by all the generators. Well, then A mod I is a one-dimensional vector space over C. That's Noetherian as a module over A. So this is about, right? This is the property of really of the category of A modules. Yeah, right. If and only if finitely generated A modules are necessarily finitely presented and necessarily coherent. Cool. And I mean, we see even that finitely generated equals finitely presented is exactly enough to prove that you're Noetherian. Okay, so that's the direction this way. So the proof the other direction is, why is it that if A is an Noetherian, all finitely generated modules are also finitely presented and coherent? And this is just the statement that all submodules a Noetherian module are finitely generated, and all finitely generated modules over a Noetherian ring are Noetherian. So if I have a Noetherian ring and I have a finitely generated module over it, submodules in that module satisfy the ascending chain condition, which you can use the sort of usual proof to show that means they're finitely generated. So if I have my M here and it's finitely generated, I have a map here from a direct sum of the p's. This is a Noetherian module, so all submodules of it are finitely generated. So in particular, the kernel here is finitely generated, and I can take my right here. All right, great. And I'm also using the M, right? Even if this map isn't surjective, because M is finitely generated over a Noetherian ring, it's Noetherian. And so all of its submodules are finitely generated. Okay. So why did I make all these notions? I mean, in part just to be persnickety, but I think it is kind of helpful, even in the Noetherian case, to kind of think about why you have to check that all of these things kind of play together. All right, and one useful thing to know, so coherent modules form a abelian category. Now, I never really defined abelian category, so it's a little unfair to state the theorem this way. The important content here is that the kernel and co-kernel of a map between coherent modules is coherent. So if my ring is Noetherian, this applies to finitely generated modules. That they form an abelian category, and the kernel and co-kernel of a map between finitely generated modules is finitely generated. But we see from these examples with non-Noetherian rings that that wouldn't work, right? A non-Noetherian ring is not coherent as a module over itself. Yeah. Yeah, sorry. Coherent A modules. So the point is, even if A is not Noetherian, you can still talk about coherent modules forming an abelian category, whereas finitely generated modules or finitely presented modules wouldn't. And it's exactly right. You can sort of prove that, like, if finitely generated modules form an abelian category, you exactly see in this, oh, that could only work if all ideals are finitely generated.
So in every
Yes. So a finite direct sum of coherent modules is coherent. Sorry, what would fail? I mean, the thing that fails is just that the kernel and co-kernel of maps between finitely generated modules won't necessarily be finitely generated. So it's not an abelian category because of that. Right? Somehow, like, you would somehow have to kind of, what would it mean to try to make finitely generated modules into a Abelian category? You'd have to have some kind of notion of the finitely generated part of the kernel, right? And that just wouldn't work because like infinitely generated things are still like a limit of finitely generated things, right? So this sometimes happens in kind of these categories with finiteness conditions, that you kind of want an object that has that finiteness condition, but you just can't do it because somehow the thing you want is some limit of things in your category that doesn't lie in the actual subcategory. Yeah, module homomorphisms. Yeah, I mean, the point is all modules form an abelian category, but some subcategories of that won't be closed under kernels and co-kernels, and so it won't give you an abelian category. Um, well, I think what I was exactly saying is every object is profinitely generated. It's generate, right? Every module is a union of finitely generated modules. So, right, the profinite would mean that you're an inverse limit of finitely generated things. So, I mean, the problem is like the kernel is a limit. It's effectively like kind of the union of all the things that map in such that you get zero. Um, and the category of finitely generated modules has limits that don't exist, right? So in the category of all modules, I think you should be able to take an arbitrary limit, but you might take a limit of finitely generated things and get something that isn't finitely generated, like taking an infinite direct sum. Or I'm doing the direct product, doesn't matter. Either way, you're going to blow up being finitely generated. Okay. So as usual, now that we have quasi-coherent sheaves, right? Quasi-coherent sheaves are sheaves that sort of locally look like they come from a module. So any property of modules you can transport over to quasi-coherent sheaves. So a quasi-coherent sheaf is, just to make this interesting, finite type, finitely presented, or coherent if when I take my quasi-coherent sheaf and I restrict it to an affine open, then I get this sheafified module for either finitely generated, finitely presented, or coherent. Okay, and I should emphasize the vast majority of the time you are thinking about a Noetherian ring. And so if the scheme X is Noetherian, or even locally Noetherian, these are all equivalent. And for whatever random linguistic reason, in that situation, people will almost always say finitely generated for the modules and almost always say coherent for the sheaves. So you would only mention finite type or finitely presented sheaves if, usually you would only do that for a non-Noetherian scheme. There might be some situation where for some reason you were emphasizing that property and you would say that. But the vast, vast majority of the time, you will hear people say coherent sheaf. And you will probably even encounter someone say, oh yeah, coherent sheaf, that's a quasi-coherent sheaf where locally it looks like a finitely generated module, which is true on a locally Noetherian scheme, but not true in general. And I am maybe not quite as amped up about as Vakil is about this point, but he makes a good point that you should actually be careful about this. Um, theorem. So, I mean, I would say this is for all you, affine, but theorem, enough to check any of these for one cover. And the proof is the same proof as all the proofs we've done for like the last 3 classes, which is it's the affine communication lemma. You prove that if you have a module over a ring such that when you take generators of the ring as an ideal, you localize at each one of those. If you're finitely generated or finitely presented or coherent after doing those localizations, then the original module was finitely generated, finitely presented, or coherent. So yeah. Yeah, for one affine cover. So there's sort of a long list of properties where when you define them, you say, ah, this holds for any affine, and then you prove, oh, it's actually enough to check this on one affine cover. And again, you might often see that as the definition, and if people don't always agree about what's the definition and what's the sort of underlying property. Okay. So maybe I'll just mention here, last time we talked about vector fields. On P1. So those were actually a coherent sheaf, right? We found that we had this sheaf of vector fields. And when we restricted it to U1 or restricted it to U0, we actually got a free module of rank 1. So on each of these affine open subsets, it was not just a finitely generated module, it was actually a free module of rank 1. So there's an even stronger word I could use here, which is that this is locally free. Meaning a coherent sheaf such that, now this is actually important for some open cover. When I take this guy and I restrict it to each of the sets in the cover, I get a free module. Because actually being a free module doesn't glue well with respect to localization. So for example, if R is a Dedekind domain, and I in R is a non-principal ideal, the sheaf I twiddle is locally free, but not on the whole thing. This is just an important sort of subclass of coherent sheaves. They're the ones that kind of like vector bundles. So any construction that gave you a vector bundle in kind of differential geometry, you can often use to get a locally free sheaf in this situation. And people will often use the word vector bundle to mean locally free sheaf. Yes. Yes, that's the same, right? I mean, if you have an open neighborhood that's not like a Noetherian scheme, or always every point has a neighborhood that's Noetherian, right? Like a locally Noetherian scheme, that means one where every point has a neighborhood that's isomorphic to spec of a Noetherian ring, right? So exactly what I'm doing here is I actually know by the affine communication lemma that if my scheme is locally Noetherian, that means that this U is spec of a Noetherian ring. And we know that finitely generated, finitely presented, and coherent are the same for Noetherian rings. All right. Ooh, okay. What do I want to do? All right, trying to decide whether I just accept that I'm slipping back a class or not. Let's try not to slip back a class. Yep. Well, then it's a free module, right? A principal ideal is by definition an ideal which is free as a module, free of rank one as a module, right? So exactly what's happening here is if I localize, then I get a free module, right? Um, you could also define this by saying that the stalk at every point is a free module over the local ring at the stalk, which is usually what you see in commutative algebra as the definition of locally free. So, I mean, right, I should say, like, right, so for example, in our commutative algebra class, we talked about invertible modules. Those are modules which, when you turn them into coherent sheaves, are locally free of rank one. Because when you take their stalk, you get a free module of rank one over a stalk of O. But those isomorphisms don't glue together correctly. And that happens a lot on schemes that aren't affine, but it even happens on schemes that are affine. Right? You could then also start having these issues of, right, these vector fields. I mean, it definitely was not just a copy of the structure sheet we saw because it had more sections than the structure sheet. But locally, it looks like the structure sheet. So here, sort of the complication was in how affine schemes glue together. I just wanted to emphasize that that can happen even when you're gluing an affine scheme out of two affine subschemes. All right. So how do we think about the geometry of these guys? And I'm just going to assume for the rest of this class that I'm on a Noetherian scheme. Well, of course, in order to do that, first we should think about the geometry of finitely generated modules on Noetherian rings. And there's sort of there's several important kind of geometric things assigned to these. So the first of these is the support. So the support of M, that just means all the prime ideals thought of as points in spec. So this is my sorry, my finitely generated module M over my ring A. So this is in points in spec A, such that when I localize this module dot prime, I get something non-zero. So, right, like the kind of thing you should think about is if I look at spec Z, if I looked at Z mod PZ, well, if I localize any prime other than P, I get zero because I invert P. So I have all my primes here. Here's the prime ideal associated to P. And this coherent sheaf just kind of sits like a skyscraper here at the point P and is zero everywhere else. All right, and its stock at that point is Z mod PZ. I could more generally take ZP to the N, and I would get the same thing here. It would just get a little thicker every time I increased N, right? Whereas if I looked at Z, then I would get a really big, complicated sheaf. The stock at every point would be the localization of the integers at that prime. So it would be a big, complicated stock. So the support of this guy is just a single prime. The support of this guy is everything. But if you think about, for example, this espace-tal, like it's really literally, the points that are hit by the map from the espace-tal, right? It's just the points where, or by non-zero elements of the espace-tal, I should say. Okay, cool. So that's nice, but there's a sort of more refined way of thinking about this. So, for example, if I look at the support of the whole ring, then I get everything. Right? If I look at the support of A mod some ideal, I get the vanishing set, of that ideal. Just kind of basic things to think about. And one kind of helpful notation is if I have an element of my module, then I can also think about the support of that. So I could define that to be the primes such that the image of M in this localization is not zero. Right? So for example, if I took any integer, its support on integers would be everything. But I could do something dumb like take Z plus Z mod PZ. Right? Then I would be taking these guys together. If I took an element of this factor, it would have support being the whole spec. If I took an element of this factor, it would have support being a single P. All right, another way to say this is it's the support of the submodule generated by M. Right? By these usual theorems about taking localization, commuting with taking kernels and images and everything. Right? The localization of A times M is the submodule generated by M in the localization. All right. Now, I can sort of decompose this support further by defining the set of associated primes. And I'm sorry, it's just true. The abbreviation we use for this is ASS. I don't know what to tell you. It wasn't very good planning, but probably it was done by Germans or something. Okay. So I can look at the associated primes of a module. And there's a nice geometric way to define it. So you'll usually see this defined in sort of some different ways in algebra. But this is exactly the primes, so I'm defining this as a subset of spec. I'm taking these primes and thinking of them as points in spec, such that the vanishing set of P is equal to the support of some element of my module. Right. So Bakil himself says, well, I'm going to list like a long series of these properties. So we'll see kind of how much of these we have time to discuss. So one thing to note is that F in A is a zero divisor in M. So that means there exists a non-zero element of M such that F times M equals 0. If and only if F lies in one of the associated primes. Oh yeah, sorry. Yeah. Sorry, I have this problem of I started using R at the beginning of the class, and Vakil always uses A, and sometimes he overrides my brain programming, and sometimes I override his. Um, uh, no, it's exactly the same. So another way to define associated primes is that C is an associated prime if and only if there exists an element of the module such that P is exactly the annihilator of M. And you can see how this would be related to this point about support. So if P is the annihilator of M, then obviously that guy gives me a section whose support is this guy. It's a little bit more work to go the other way. But the usual trick you use is I have some M, I look at the annihilator of this M. Well, if that's not already a prime ideal, then by Noether's theorem, it contains a product of these prime ideals. And if you sort of think about this, you can use this to eventually multiply M by some stuff, which will get you exactly a prime divisor here. All right. Cool. Sorry, what the set of associated primes? The support is always closed. I want to be careful about this. You might need that M is finitely generated. Right, right. Infinite union of closed sets isn't closed, but right, the support of a single element is going to exactly be V of the annihilator. And so then if you're finitely generated, then you're going to be a finite union of closed sets and you're closed. All right, so what are some other important things to know about this? The generic points of components of sup m are all associated primes. And I should note, right, there's a section in Buckhill where he states all this stuff, and then he sort of spends several pages proving it. This isn't a commutative algebra class, so I'm sort of not going to go through all the proofs. Most of them kind of, once you know this trick of looking at these product of primes, everything kind of follows naturally. Yeah. So, right. If I look at the associated primes in A of A mod and ideal, then those are exactly the primes such that there's a P primary ideal in the primary decomposition of I. So let me try to write some actual words here. If I look at these primes in here, there exist PI, PI primary ideals such that I is equal to the intersection of these primary ideals. Great, and exactly what happens here is that, yeah, let me not try to talk through this too much, but right, somehow the associated primes are you want to look for things in A mod I, such that when you multiply them by a prime ideal, you get 0. And if you think that through, you'll see that you have to get these guys. So the kind of thing you should think about, because these aren't all things, so there do exist, there can be elements of this associated prime set such that they're not generic points of components. And one way to say this is that V of P lies inside V of Q for Q also in the associated primes. Right, these are called embedded primes. So if I come back to this example, right, if I took the direct sum of Z and Z mod P to the NZ, then my associated primes would be 0, because any non-zero element of Z has annihilator 0, and P, because there's an element of Z mod P to the N, which is annihilated by P. So I would get the prime P and the prime 0. And what this is sort of telling me is, well, I have my support, which is this whole thing, and then I have one point where something a little more exciting happens. That's somehow different from what's happening at the other points. And this guy being an associated prime is telling me something different happens here. In particular, there are sections of the sheaf that are only supported at this point. All right, so let's just talk about one kind of basic example, because we're almost out of time. I can take C adjoint xy, and I can mod out by yx squared, y squared x. So in this case, the spectrum is this cross, right? This is just, if I mod it out by the radical here, I would just get C of xy mod x times y. But what I'm doing is I'm keeping an extra nilpotent element here, which is x times y, right? I haven't set x times y to 0, but of course its square is 0. So if I took the associated primes, I would get the x-axis and the y-axis, and I would also get the point where they intersect, right? Because this is the annihilator of y, right? If I multiply y by something, and this did I get this right? I did get this right. This is the annihilator of x. If I multiply x by something that vanishes on the x-axis, I get 0. This is the annihilator of y. If I multiply y by something that vanishes from the y-axis, I get 0. And this is the annihilator of xy, right? I've exactly arranged this so xy would be a non-zero element of this ring, but if I multiply it by x or I multiply it by y, I get 0. So exactly what this is telling me is, well, I didn't just take the reduced ring associated to this guy, I also added some nilpotent fuzz at the origin. And this embedded prime exactly picks up that nilpotent fuzz. So that's usually what embedded primes are kind of capturing, is that things kind of got more nilpotent at that point, which is exactly expressed by there being a section that's only supported there, which is nilpotent and vanishes away from this point. And I mean, there's nothing kind of sacred about the origin here. I also could have instead put some nilpotent fuzz here if I wanted to, by putting in some slightly different relations, which I'm not going to worry about right now, which you could probably guess you would want to instead arrange that the ideal x and y plus 1 was an associated prime. So you would want to find something that was killed by these guys. Yeah. If we, oh, if you want, if I take, no, if I take C of xy mod x squared y squared, that's supported as a single point. That's a finite dimensional ring. So here, the picture would be just this guy, and the only associated prime is y. So I exactly did this so I wouldn't kill all the powers of x or all the powers of y, which is why I still have the axes. It's helpful to sort of draw this picture of what monomials did I kill and which ones I didn't, right? So this corresponds to the picture where I did this. And what you suggested corresponds to the picture where I do that. I kill all of the monomials past here. So, I mean, there's also an interesting question of how do you kind of visualize, right? There are lots of quotients of C of xy by nilpotent ideals that somehow have some different geometry, but all have a single point. But you should think of that point as being slightly fuzzy and think of that fuzz as having some kind of shape, right? So this is sort of slightly squarer fuzz. I could have also modded out by C of xy mod x squared xy and y squared, and that would make this fuzz sort of slightly more rotationally symmetric. It's kind of a weird picture, right? If I mod out by more stuff, that means I have less fuzz, right? But you can sort of think about it maybe a little more precisely as like when I have a function on here, I remember part of the Taylor series, right? And so for this guy, I'm remembering 4 terms of the Taylor series. Whereas if I take this guy, I'm cutting this corner off and I'm remembering one less term in the Taylor series. All right. I think that's all I have time for. So we'll talk more about this stuff next time.